Now comes the thing that lots of people don't understand, and no faculty will ever understand, and some younger people might sometimes. There we are. When you know how to count 3-period states, 4-period states, 5-period states, it's stupid to write the table of these things. It's an infinite table. Is there some convenient, powerful way of stating it? And we know this in lots of mathematical problems. If you can write a generating function that generates all these numbers, but it's simple, then that's what we do. In the case of problems with translational invariance, in this case invariance in time, the generating function is called zeta function, just for historical reasons, because it mimics Riemann zeta function, but it's not that. Natural generating function says, I have to count how many states there are. Now, because of translational invariant, if I have a lattice state, I can move it by one step, and it'll look different, but it's actually the same step, just translated. So there'll be n copies of each one of them. So you have to divide it by n, because you want to count distinct states. Distinct states are called orbits. It's a distinction between periodic orbit and periodic point. So you have to divide by n, and when you divide by n, that looks like expansion of a logarithm. Now, that's typical shape. So you want to exponentiate the logarithm to get a nice generating function. And in this case, it's beautiful. You stick your number in here. These are two logs. You can do them, and you find that topological zeta function, the one that counts the states, just a rational polynomial. The numerator tells you that there are s different states, primitive states, and these are the intervals we saw in Bernoulli. And this little guy has to be there because I'm not allowed to overcount the point at the origin, so that's what he does. So this is periodic orbit theory, and now if you click on this link, you will get a nice wrap video. So what it does, it counts prime orbits, what for each set of physical states which are same modular translation. That's it. You have solved the theory, and then Chaos book in mere 300 or 400 pages gets to this point and teaches you how to compute expectation value of any observable of chaotic systems. And now you know everything you need to know. And the idea is always the same for field theories. You have to find all possible solutions of your law, and you solve them by finding fixed points in this large dimensional phase space. Each fixed point has a global stability that's called a Hill matrix, and the fundamental fact enables you to use that to find the number of orbits, but you can do much more. You can get a zeta function. Once you have a zeta functions, you have solved the problem. Everything can be predicted. I write the zeta function, I put these numbers in, and I get a beautiful explicit formula for the topological zeta function. And this is all you need to know about CatMap. Now, when they teach you this in books, you look at some magical partitions. You don't need any of that nonsense. When you know lattice, it just takes care of it.